Okay, so we can start for today's session. Hi, I'm Smita Mundu. I'm a PMRF scholar of IIT Madras of Department of Chemical Engineering. So in today's session, we will be discussing on the screening part, that is the size analysis of different kind of particles in a mixture. So we can see that when we uh, in the last class we have defined that how the particle size and particle shapes are important to analyze when this is a mixture of particles. So in a sample which consists of uniform particles of diameter dp, the total volume of the particle will be mass upon density of the particle, where m depends the total mass of the sample and density, that means the total density of the particles. Since the volume of one particle we denote it as Vp, the number of particles present in the sample, it can be calculated easily by this equation, that is number of particles will be mass divided by density into volume, that is gram divided by gram gram per cc into cc, that is unitless. So we get the number of total particles present in the mixture. Now we want to calculate the total surface area of the particle in terms of the sphericity. So in the last class we have defined what is the definition for sphericity. So in this class we want to derive the expression that how we should calculate the total surface area of the particle. It denotes that a specific surface area for one particle into number of particles. That what we know. So when we substitute this equation over that sphericity equation in the last class, we will get a simple equation like this. It denotes the total surface area of the particles in terms of the sphericity, and there will be other terms related to the particle diameter, density, and the mass of the total mass of the sample. So, to calculate the number of particles and the surface area of the particles in a mixture of different sizes and density of the particle, the mixture will be sorted into fractions and each constant density and approximately constant size. So, when we divide it into different fractions, so in those fractions we get generally by the mechanism of screening. So each fraction will be weighed separately, or the individual particles in the fractions. It can be counted or measured by any kind of available methods. So this equation 1, that is the number of particles present in the sample, and the equation 2, which represents the total surface area of the particle, can be applied for each of the fraction, and at the result we can just add up those values to get the overall number of particles in the mixture and overall surface area of the sample or in the particles in the sample. So here the main terms it comes, that is screening. We need to do screening so that we can separate our sample particles depending on their size. So screening is the separation of a mixture of solid particles, various sizes they have, into two or more fractions by means of a screening surface. So in screening, a mixture of solid particles of various sizes is dropped onto the screening surface. So the material that passed through the screen surface will be called undersize of the screen, and that will be denoted as minus. Suppose your screen size is 8 mesh. So the this is your screen, there will be some opening. So when you feed some solid material, so some solid will pass through the screen. So this what it passed through, it will be known as undersize, that will be known as -8, and the oversize, it will remain, and that will be denoted as +8. So this is how we denote when we do the screening analysis. So the material that can be separated into fractions based upon the sizes, the fraction in which both maximum and minimum particle sizes are known by passing it through a series of screens of different sizes. So you can see this is the visual demonstration that how the screens are stacked one upon another, and we do the size analysis, and how it looks like. So this is the commercial or um, available screens that we use in laboratory as well as industry. But it should be in mind that in industry it doesn't look like this is small and this kind of this is the simplest version. The screens that will be used in industry, that can be grizzly or trommels. So this kind of screens I will be discussing at the last of this class. So suppose you are doing the laboratory analysis for the size of mixture of particles of different sizes. So you want to analyze it how? So this is the this is the screen shaker, this equipment. So we stacked the screen one after another in a way of this is the top one will be the um, bigger screen opening, and the bottom one will be the pan. Pan means that will be just a pan, there will be no mesh. So when we do the size analysis, suppose we have stacked the screens one after another, and we are feeding the solid particles from the above, and there will be this equipment is nothing but shaker. So this will shake in this direction. So it or any kind of movement it can give, so it will be shaked through the screen and the particles will move onto the screen. So suppose this first top mesh, that will be bigger mesh, you can see by visually you can notice, and the last one will be the smaller mesh. So in each screen, onto the screen, there will be some leftover remaining materials will be there. Suppose it is noting as x1, the fraction of feed that is um, being retained onto the screen surface, that is known as x1. So in this way, in each of the fractions that is being written onto the each of the screens, and that those are fractions are denoted as x1 to x6. Okay, so in the next part, as we already have discussed that how you are going to calculate the total surface area of the particle in terms of the sphericity. So this equation we discussed in the first slide. So now we will move that how we want to calculate the specific surface area for the mixture. So surface area of the particle in each fractions from the screening that we got may be calculated, and those results can be added up to give you the specific surface for the sample. So in the whole system, if the density and the sphericity remain same and we assume it to be constant, then we can calculate the AW, which is known as specific surface of the mixture. So in each fraction, it will be the same, like x into this m represent total mass. So x1, this fraction will be x1 will be the mass of this total mass, fraction of this total mass. So that's why it is x1 and other things remains constant. And this particle diameter is average particle diameter. It will be also denoting for that fraction 1. So in that way, if the fraction, if we are setting the screens, suppose 5 or 6 screen are stacked one after another, then we will get approx 7 to 8 fractions, and those will be add up. Like for that case, it will be like 6 by pi s rho p. Summation of 1 is I equals to 8 and xi by dpi. So you should note down that when we take the DPI, how it will be calculated. That we will discuss when a numerical will be there. So this average particle diameter is nothing but we are taking the arithmetic average of the smallest and largest particle diameter in increment. So we already discussed that what is the specific surface of the mixture and how you will calculate this. You should remember this formula. And then the average particle size, also you want to, like, you have different particle sizes in a mixture. So you want to know what is the average particle size of that your sample. So that is defined in a various way through various definition. First one is volume surface mean diameter. Obviously, it is related to specific surface area that we discussed just now. So it will be in terms of volume surface, it will be in terms of the specific surface area. So from this equation and this equation, we will get to know this expression. And this expression can be further simplified in terms of this. You should remember this formula. The arithmetic mean diameter, it is also in a form of this simpler form, and this particular definition for average particle size, you can also calculate what is the average particle size of the mixture. This is known as arithmetic mean diameter. Similarly, there is one another definition for mass mean diameter, that is summation of fraction into average particle diameter for n number of fraction. You have to just add up. And the volume mean diameter, that is uh, volume is, this term is introduced, and this is the expression for overall. So these derivations are not that much important. You can just remember that I think these derivations have already discussed in a detail in the actual NPTEL lecture for this screening session. So you can just go through those derivation. But in this class, I would like to have focus that these are the formula. You should make a chart and you should remember because there will be some numerical that will just give you the mesh, the screens, their retained weight percent of the samples onto the screen, and you must be asked to calculate. Suppose what will be the volume mean diameter. So for that case, you just remember this formula and you can just process those data afterwards. So for samples consisting of uniform particles, these average diameters will be the same, of course, more or less same. But if your sample consists of various mixture of particles, then this each of the value from this diameter might not be the same, and that may differ from one another. So the next part, that is the you want to calculate the number of particles in the mixture. So you just go through this first equation that we are using in this lecture, that is number of particles is defined in such way, and Bp, volume of the particle, can be directly proportional to average particle diameter, that cube. Um, so you can just calculate an expression which represents the number of particle in a mixture, that is 1 upon A into rho of the density of the particle and the volumetric volume mean diameter of the particles in the sample, where A represents the volume shape factor and A is independent of the size. So we have discussed that how the different particle size for a mixture is being defined. There will be different definition for that, and now we will know that how the size analysis are occurring. So in reality, the screening is more commonly adopted in any kind of process industry. So there they can process dry particulate solid, or it can be a wet operation, wet particulate solid separation. So what is the reason why we want to do the screening part? That why we can't just get our sample or any kind of ore material, or suppose you are handling the coal material, you can simply just after simply getting the your sample, you can simply go for the size reduction or any kind of other operations, but that may lead to many kind of obstacle in the process, whole process. So the screening operation is very important in industry, that needs to be carried out in order to remove the fines from a feed material before reduction equipment, before introduction of the sample into the reduction equipment, just like jaw crusher, ball mill, or rod mill, and then prevent an incompletely crushed material, just like oversized material, from entering into any kind of important unit operation equipment. So we don't want to introduce such bigger size or oversized material into any process equipment, because every process equipment has some criteria of the feed size. Um Suppose you are just operating any blast furnace to make the steel, there will be steel. So in that case, the coal that will be introduced, there should be a particular feed size should be maintained. There are some certain specifications, so for that case these kind of screening operations are very important. Then produce a commercial or process grade material to meet the specific particle size limit. So these are the main reason that why screening operation should be carried out in industrial sector as well. And we also need to remove sometimes the excess fine materials from the finished product, because there are also some requirement that that material, before selling it to the market, we need to remove excess fine material um, from the sample. So that time we also go for screening operation. So now we will discuss that how the classifications of the screening are generally we do based upon the performances. The objective of a screen is to accept a mixture of various sizes of grains and to separate it into two fractions. Namely, there will be underflow and overflow that we already discussed. This overflow is also known as oversize. The underflow is the one that passed through the screen, and the overflow is the rejected by the screen or that is retained onto the surface of the screen. So, an ideal screen is the one which sharply separates the feed mixture in such way that the smallest particle is in the overflow is just larger than the largest particle in the underflow. So, we were discussing about the classification of the screening. So, when we talk about the ideal screening, so it generally sharply separates the feed mixture in such a way that the smallest particle in the overflow section is just larger than the largest particle in the underflow section. So, the ideal separation defines a cut diameter, that is DPC, which is typically a particle dimension it denotes, which makes the point of separation between the undersize and the oversize, and which is nearly equal to the mesh sizing or the mesh opening of the screen. So, this definition will be clear when we will show the graph for the size analysis. So you can see this one is what it represents the ideal screening. There will be a um, sharp differentiation between the overflow and the underflow. So here the fraction A represents all particles larger than dpc, which is the cut point diameter, and the fraction B denotes all the particles are smaller than the diameter dpc. So here you see there is no overlapping and there is a particular cut diameter. For that you can see that there is a exact sharp separation between the overflow and the underflow. But when you go for ideal screening and the screen size analysis you do, then you can see that in terms of the sphericity and the particle diameter, there is a curve for oversize and undersize, and it overlaps in a certain at like there is no overlap, but they have the one last point of the curve A and the first point of the curve B, they have the same abscissa. So you can see that it represents a very sharp separation between the overflow and underflow that represents the ideal screening. But in general or in reality, this kind of ideal separation is not possible. So what we get, this kind of overlap graphs we get, where um, this is the actual screening it represents, and it do not yield any sharp separation. So the overflow is found to contain the particles smaller than the cut diameter. It also contained some particles which is smaller than the cut diameter, and the underflow can also contain particles larger than the cut diameter. So here is the reason where you will get these two kind of deviation, and this deviation denotes that this is not the ideal screening, it is the actual screening. There is some overlap that that some of the particles that is still smaller in size, but still it is retaining onto the surface of screen. So this is not ideal case, right? So in actual or in actual situation, this kind of things we experience. So with a standard testing screen, it is possible to get the closest separation in case of the spherical particle. But in reality, all the particles are not spherical in size. So we need to very carefully, we need to check, and at the maximum way we can do the actual screening, but we will get ultimately this kind of graph where we will get a overlap region. So you can see this graph is for the feed, complete feed, and this is for the oversize and this is for the undersize graph. So from here, uh, this one, it represents the fraction of any suppose a fraction of a material into the oversize, fraction of material into the feed material, and fraction of the material into the desired material into the bottom part of the screen. So now we will discuss what are the types of standard screens we use or we follow. So first one is like for carrying out this screening analysis, standard screens that we use either be Taylor standard screen series or US SIP series or Indian standard SIP series. The test sieves with square openings are constructed maybe woven wire screens, the mesh and the dimensions of which are standardized before. Every screen is identified by its mesh per inch. So when we consider a coarser screen, that means the term mesh refers here the distance between two adjacent rod or wires. While in fine screens, the mesh is the number of openings per linear inch, counting from the center of any wire to a point exactly 1 inch distant. Suppose a 200 mesh screen will have 200 openings per linear inch. So the minimum clear space between the edges of the opening in the screening surface will termed as screen aperture. That is also known as screen size opening. So the thing that you need to remember in this case and never get confused about it, that is the higher the mesh number, there will be smaller aperture. You can understand from this picture that this denotes a screen segment. Suppose, so here we can see, suppose this is 1 inch and there will be 1, 2, 3, 4, 5, 6. Six openings are there. So that will be known as 6 mesh. And this one opening is known as the screen opening or aperture. Or as simple as that, this is the wire diameter. Suppose in this also they have denoted 1, 2, 3, 4. 4 openings are there in a 1 inch linear inch. So that will be 4 mesh. The mesh number is 4. So in this way we calculate and we marked the standard for the screens, and according to our requirement we will select those screen and we will make a stack out of the screens and do the screening analysis. So first type of screening standard, that is Taylor standard scale, which is based on the size of opening in the wire cloth, which have 200 openings per linear inch. So the diameter of the wire that is used for 200 mesh screen is 0.0021 inch, which is also known as, which is also can be converted to millimeter. So the opening is 1 by 20, that is, sorry, 1 by 200, that is the mesh number, minus of this wire diameter, that will give you the opening of the screen. So the ratio between the adjacent sizes of the screen scale is root 2. Thus the area of the opening of each sheet is nothing but double those of the next finer screen. Therefore, suppose a coarser screen 150 mesh, that means in a one linear inch, there will be 150 opening. Whereas 200 mesh means one linear inch, there will be 200 openings. So which one is more bigger opening? Corsair screen is 150 mesh and the final screen is 200 mesh. So for that, when we want to calculate the opening for Corsair screen, that is 150 screen, 150 mesh, we will simply multiply root 2 into the opening of the 200 mesh. So thus we can calculate. The area of the opening in any one screen is exactly twice that of the opening of the screen below it, because that is more coarser. Testing sieves of the Taylor standard sieve series are used to determine the efficiency of screening equipment and the work of crushing and grinding machinery. So this is the chart for the Taylor sieve series analysis. So you can see that the mesh size is going increasing in downwards. So we are taking out 200 mesh, which is also known 74 micron mesh, 74 micron screen. So for that the opening is 0.0074 millimeter. So if you go above Corsair 150, for 150 it will be 0.074 into root 2. So what will be the value for that? Can you please calculate? 0.074 into root 2, that is 0.104, that is this one. So if you go from here to here, you just simply divide it by root, uh, you can simply divide by root 2. So that's why you can follow the Taylor series, sieve series, for calculating any aperture size based upon the available data. Is there any question as of now? You can ask. Okay. So we will go to the next topic, that is type of screen analysis. So there will be two types of screen analysis. One is differential analysis and another one is the cumulative analysis. So the differential analysis denotes the screen analysis in which the weight fraction of the material that is retained onto the surface of each screen is reported in a tabular format or graphical format as a function of mesh size or screen opening. That is known as differential analysis. Whereas cumulative analysis, that is obviously dependent on the differential analysis, and it will be the cumulative weight fractions of the material that will be retained or passing through. That will be different, like it can be cumulative oversize and it can be cumulative undersize of each screen is reported in a also tabular or graphical format as a function of screen opening, that is known as cumulative analysis. So the results of a screen analysis can be reported in a tabular format or to show that for each for this screen for this screen, what is the average particle size, what is the screen opening, and what will be the refraction of sample retained onto the screen. Also we can do what is the fraction of sample that will be passing through. We can also do this kind of calculations. So this para we already discussed that how we denote oversize and undersize of a screen. Oversize is denoted by plus of that mesh number and undersize denotes that minus of that mesh number. So the average particle size of the material retained on any particular screen is calculated as a arithmetic mean of the two screen opening that is used to obtain the fraction, that is d1 plus d2 by 2. Simple arithmetic mean. So next we will focus on the differential screen analysis. That is, suppose this is one the standard detailed screen scale. The mesh is given and the microns is denoting, and the millimeter is the opening size that it denotes. So now we can do this simple calculation, that is the mesh. These are the meshes suppose we you have taken for the screen analysis from mesh number 6 to mesh number 200. The screen openings, how you will calculate the screen opening? Suppose for mesh number 6 you point out this one, mesh number 6. What is the screen opening in microns? That is 3327. For mesh number 8, what is the micron? 2362. So for that, the finer mesh is 8. So we will take this value. So a screen opening in microns, we will take the finer screen for this. Similarly, for 10, it is 1651. Around nearly it can vary little bit. So it is 1652. So there you fill the data, and now the average particle size in microns, suppose that will be calculated based on the suppose this is 6 and 8, this is 3327 plus 2362 divided by 2, that will be 2845. So in this way you calculate the average particle size for this column, and the weight fraction retained, it will be it is 0.017. It will be this column you will fill the data from the experimental analysis. So you can see all the weight fractions from here that will add up to 1. Weight fractions will be 1. So now the cumulative analysis that table we made, that is for the differential analysis, that is we will plot the graph for weight percent retained in a function of average particle size, and the cumulative analysis will be obtained from the differential analysis by adding cumulatively the individual weight fractions of material retained onto the screen, starting with that retained on the largest mesh, and that will consider um, depending on the screen opening. So we define the phi as cumulative analysis, and that will be the summation of this weight fractions for different 1 to number of screen you have stacked one after another. That will be, you have to go in a cumulative way. So the cumulative analysis, it will represent the relation between the phi and the screen opening. So the ultimately that will add up to 1 at the last. So now we can calculate the same problem that we discussed before one slide, that we have calculated the differential, we have made a table for the differential screen analysis. Now from there we want to convert it to the cumulative screen analysis data. So the same screen, you write down the screen, and you also write down the screen openings in micron for individual. So from that, the cumulative fractions for the oversize will be for 6 mesh 6. Suppose these are the screens. This is 6, this is 8, this one is 10, this one is 14. So the feed is being fed up. So here we have experienced from the experimental data, there is no retained feed fraction onto the number 6 screen. So it is 0. But we have got some amount of the fraction onto the screen 8, so that is 0.017, this one. So we will just cumulative way, we will do the summation, like 0 plus this one, we will get this. Next step, that will be this plus this, that will be this. So that's why when you add up, so at the last there will be pen, and it will maintain 1. That is the way we do the screen analysis in a cumulative way. So phi is the cumulative fraction retained onto the screen, and what is the passing, that we can do 1 minus of phi. So this graph represents the fractional particle size distribution. So here the distribution table we showed, depending on that these data are being plotted. So we can see that the mid-size particle range is around this one, around 1410 micron. Similarly, for the cumulative particle size distribution, so these are the cumulative fraction up to 1, and these are the screen opening in microns. So this represents cumulative uh, under undersize material, and this represent cumulative oversize material, that goes up to 0 when we increase the screen opening size. So here we can see, like, what is, we want to calculate this 3 factor, that is D10, D50 and D90. D50 is the when there is this oversize and undersize graph, these two intersects. These two intersects, that represent D50. So it is around 1249 micron. You want to calculate the D10, so this is like 0 and 0.2, so in between there will be 0.1. You intersect with this you plot this graph, and this graph denotes around 500. A little bit different it can be. So 511 is the micron that represents 10, that represents 10% of the particles. Those are smaller than this size. And 9 D90 is the point 9 is there, point 0.9. So you drag and you intersect and you draw a line, vertical line. It will represent 2111 micron. So this one is the 90% of the particles are smaller than this size. So in this way you can calculate. These are the data important, very important for the screen analysis. Now we will go with the first question for this session. So I would like to request you to participate in solving this question. This question is calculate the volume surface mean diameter for the material, and the size distribution table is represented here. So from there you would like to do the volume surface mean diameter. It will be nice that you remember the formula for volume surface mean diameter that we discussed in the class today. This is the formula for volume surface mean diameter, 1 upon summation of xi by dpi. Now you calculate. At first you make the table. This is the diameter range. Depending on that you calculate the average diameter, obviously in microns these are, and the weight fraction, and at the last you calculate xi by dpi. So this range denotes 10 to 20. The average diameter will be 15, and the weight fraction in that interval of xi, that will be 3 minus 0 by 100. In that way 20, 30, 30, 40, 40, 50, 40, 80, 80, 100, 100, 150. These are the data, and you can calculate the mean 25, 35, 60. This one is 60, this one is 90, and this one is 125. So you can just simply do xi by dpn. You will get the data 0.03 by 15, 0.002. In that way you calculate all the data and it will look like summation will be xi by dpi. What will be the summation? 0.01962. So at last we need to calculate by this equation 1 by 0.01962 and it will be 50.97 around this much micron. If there is any question regarding this whole procedure, you can just simply raise the question. We are discussing about the uh, first our numerical for this session. So if there is any question regarding this solution, you can simply raise your query. We have calculated the volume surface mean diameter for this distribution. And what is the procedure we followed? We make the range of the diameter. From that we calculated the mean. We calculated the mean diameter for that range. From that we also calculated the weight fraction in that interval, that is represented as xi, and then we calculated the rest of the portion according to the formula. So we will move on to the next topic, that is the capacity and the effectiveness calculation for the screens. So the capacity of a screen is the mass of the material that can be fed per unit time to a unit area of the screen. So this capacity and the effectiveness in screening operations are closely related. For obtaining the maximum effectiveness, the capacity must be small. For the largest capacity, obviously the effectiveness will be reduced. As the capacity and effectiveness are opposite factors, a reasonable balance must be done between them in actual industrial practice. So one can control the capacity of a screen simply by varying the mass flow rate of the feed to the screening equipment. For a given capacity, the effectiveness can be achieved depends upon the nature of the screening operation. For a given undersized particle, the overall chance of the passage through the screen is a function of number of the contacts between the particle and the screen surface. The probability of its passage in a single contact. When the screen is so much overloaded with the feed, the number of contact is very small and the probability of passage on contact will be reduced due to the interference of so many particles at once. The effectiveness is improved by reducing the capacity onto the capacity of the screen since there will be more contacts per particle when there will be minimum capacity. Better chance for the passage on each contact. The factors which tend to reduce the capacity and which tend to lower the effectiveness, those are known as blinding, cohesion of the particle to the screen surface, some oblique direction of the approach of particles to the screen surface, and some interference of bed particles with the motion of one another. Obviously, that is very important that the moisture content of the feed they adversely affect the screening operation as they can damp the particle, make the agglomeration, block the screen, and that will reduce the effectiveness of the screening. So, in this, we will try to calculate the effectiveness of the screen. So, this derivation is being elaborately mentioned here. So we will do simply the material balance over a screen to calculate the effectiveness. Suppose your feed material onto a screen consists of material A and material B, where material A is the oversize and material B is the undersized material. And F is the mass flow rate of the whole feed, D is the mass flow rate of the overflow. Suppose this is the screen. These are the openings. You are introducing feed. F is the mass flow rate and XF is the fraction of A in the feed. Some will be retained onto the screen. So this will be known as D is the mass flow rate of the overflow material, while XD is the mass fraction of the A in the overflow, and some material will pass through the screen, that will be B is the mass flow rate of the underflow and XB is the mass fraction of the material A in the underflow. So this way we have defined for the material A. We need to define also for the material B in the feed, that will be 1 minus XF, in the overflow that will be 1 minus XD, and in the underflow it will be 1 minus XB. So now after doing all of this assumption and denotation, we will go through the overall material balance over a screen. That will be feed equals to overflow plus underflow. This flow rates you are making equal or do the mass balance. So specifically when you do the material balance of material A over a screen, it will be total of material A present in the feed, that is F into XF, Material present A in the overflow, that is D into XD. Material present in the underflow, that is B into XB. So from there, when you do the substitution process, you can go through these steps, and after that we will make this kind of ratio, that is underflow by feed, that is, okay, this got changed, that is B by F equals to XD minus of XF divided by XD minus of XB. Similarly, this one is D by F, XF minus of XB and XD minus of XB. So the effectiveness of a screen, which is also known as screen efficiency, is a measure of the success of the screen which is closely separating the undersize and the oversize materials. In the case of a perfectly functioned screen, all the oversized material A would be on the overflow and all the undersized material B would be in the underflow. The screen effectiveness based on the oversized material is the ratio of the amount of the oversized material A that is actually in the overflow to that the amount of the oversized material present in the feed. So this is what I was talking about, the definition of screen effectiveness on overall material, oversized material A, that is EA equals to D into XD by F into XF, that is quantity of the oversized material in the overflow divided by quantity of the oversized material in the actual feed condition. Similarly, you can just substitute this and you can also make an expression for screen effectiveness of material B, that is EB equals to B into 1 minus XB by F into 1 minus XF. So thus we can calculate the overall effectiveness of the screen, that is E equals to EA into EB. We can do some substitution method and we can follow this final expression for calculating this overall effectiveness of the screen. Is there any question as of now that you need more clarification? You can simply ask. Then we will go to the next question, that is the screen effectiveness question that we will solve in this as a next numerical. So there is a dolomite mixture having the following screen analysis. It has been screened through a standard 100 mesh screen. So we need to calculate the effectiveness of the screen and the mass ratio of the overflow and the underflow to the feed. So you have been given this chart. So you need to calculate what will be the effectiveness of the screen. Already we have derived the expression for effectiveness of a screen. You can follow this expression and you can calculate this screen effectiveness. So at first you can calculate what is the xf, xd and xb for your case. You can calculate based upon this data, right? And let me know what is the value you are getting for this three variable. You need to understand that the in the question it has been given that it has been screened through a standard 100 mesh screen. So you need to focus up to this part for your calculation. So the value of xf will be 7.07, 16.60, 14.04 and 11.80 divided by 100. What is the value we are getting? 4951. In that way you calculate, please, and let me know what is the value of xd and xb. xd represents oversize that we are talking about and xb represent undersize. So in a
Hello,
simple
ma'am. I am audible. Ma'am, I am audible.
uh, hello, uh, can you please repeat
Yes, ma'am.
yourself?
I am audible.
Yeah, yeah.
Ma'am, so basically, you have tell us to find XF value.
Yes,
So is it 73.087?
you have to divide by whole weight of the feet, that is 100.
Yes, ma'am.
uh, you are telling the value of xf only.
Ma'am, you have find XF and XD. We have to find that. We have to find XD value.
Yes, xf, xd and xb value.
So XD value is 73.08. That's
Oh,
my question is. Is it
oh.
correct?
um, Let me do my calculation once. It is around 0.9358. So
Okay,
this,
ma'am.
so this is, maybe you can check, 13.67, 32.09, 27.12, and up to 100 mesh. Sorry, 20.70 divided by complete overflow, that is 100. So the value will get 0.9358. And also in a similar way, when we do the undersize, that xb will be 0, 0, 0 plus 2.32 divided by 100. It will be 0.0232.
Ma'am, for XD, I have calculated this. My answer is 0.8758.
You have calculated up to 100 mesh.
Yes, ma'am.
No, it is coming 0.9358 only.
Okay, ma'am.
You follow this data properly up to 100 mesh. You do the summation of this data and divide it by total. So you will get the fractions.
Ma'am, again, my answer is not varying for by your answer.
It is not matching.
Yes, ma'am.
Uh, mm, this is what it is. I don't know how you are calculating. This is simple. Like you have to do the
Ma'am,
summation.
that over, ma'am, listen, oversize value 13.67 plus 32.09 plus 27.12 plus 20.70. Okay, we have add them
Yes,
divided by 100.
yes.
Then also I am not getting perfect answer.
I had just now checked with my calculator. It is what the value is. I don't know how you are getting other value.
Yes, ma'am. Now I matched. Perfect. Your answer is perfect.
Yeah, okay. So now we can calculate the other factors. For we have to the question is we have to calculate the effectiveness of the screen. So for that we can go forward with just calculate the mass ratio of the overflow to the feed. Mass ratio of the overflow, that is D by F. That was XF minus XB divided by XD minus XB. Let me know what is the value you are getting for this. Similarly, you can calculate the value B by F, that is the mass ratio of the underflow to the feed.
Ma'am, can you please show the previous slide? Now, ma'am, show the next slide.
So you can calculate B by F. The expression is XD minus XF by XD minus XB. That you don't have to do the whole equation, you just simply do B is, you can also represent F minus D, so you have to just 1 minus of this value, so this value will be around 0.517. it will be 0.1517, and you will get the value around 0.483. Then you
Yes,
have,
ma'am, correct.
yeah, so then you have the big equation for the screen effectiveness factor. That is, I can again mention that formula: xf minus xb, xt minus xf into xt into 1 minus of xb divided by xt minus xb the whole square into 1 minus of xf into xf. You have to just put the value and you will get the overall effectiveness of the screen. The value will come around 0.9131, which represent 91.31% effective. So if you are done with that, then we can go to the next topic.
Yes, ma'am, I got the perfect answer.
Yeah, that's fine. So next we'll be discussing about the screening equipments. So this part, it is important when you deal with some ore material or those kind of coal sources in an industrial sector. So screening equipment that we generally use, that is grizzly, trommels, or shaking and vibrating screen. These are very um, widely adopted in the industry for any kind of Porzer size range or fine sizing. So in the screening operation, the coarser particles easily pass through the larger openings in a stationary surface, but when we deal with the fine particles, the screen must be agitated or must be shaped. Otherwise, they will just stack together and they will block the opening of the screen. So, for handling with very fine particles, you need to mechanically or electrically, you have to shake those screen stack, and for that you need to design those screen in such a way. So these kind of commercial screens are already available. So this is kind of a screen that is known as grizzly screen. So a grizzly is a grid of parallel metal bars. Those are framed in a inclined way in a degree of 30 to 45 degree. So they slope and therefore the path of the material which is parallel to the length of the bar. So the length of the bar may be up to 3 meter and the space between the bar it may up to 50 to 200 millimeter. So the materials of construction that is very important for handling any kind of very abrasive material. So the material of construction of these bars are manganese steel to reduce the wear during the operation. Usually the bar is shaped in such a way that its top is wider and the bottom is quite narrower, and hence the bar can be made firmly deep for strength without being choked any material that is passing through the grizzly bar. So a stationary grizzly is usually used for any kind of dry screening, but it is not satisfactory gives performance for any kind of sticky or moisture trapped, or the materials which has moisture, this kind of sticky material cannot be advisable to be treated in a stationary grizzly. So now coming to the working principle for the grizzly, so you can see that a coarser feed, say, which is like primary crusher. From a primary crusher, we get the primary crusher means jaw crusher, cone crusher. Those kind of crusher, the feed material that we are getting, those are coarser feed material. Those can be fed at the upper end of the grizzly. This feed is being fed from the upper end, and the large chunk of particles, they roll and slide to the lower end, that is the uh, tail discharge that we know, where the small lumps having the size less than the opening in the bar fall through the grid into the separate collector. So if the angle of inclination to the horizontal is greater is the output or throughput, but there will be lower in the efficiency. So you need to take care of the angle of position for this grizzly screen. Stationary inclined woven metal screens operate in the same way that separates particles from 12 to 100 mm in size. A grizzly finds its greater application in the separation of the undersize, which is generally undersize here. We get generally these are fine material, and from the primary crusher feed. So this kind of oversize. Suppose you are dealing with the jaw crusher and you got the feed product from the jaw crusher, you fed into the grizzly, and the oversize will be the perfect size maintained for the jaw crusher, and in the process the finer material that got generated or created, those will be separated from this main product. So these are the fine material that can be separated from the grizzly screen. So, a stationary grizzly is the simplest kind of separating device that we know, and it requires no power and less expensive for installation and maintenance. As the opening in the grizzly have a tendency to get blocked by wedge-shaped particles, and so the labor requirement for operating the grizzly is very high, and it is difficult to change the opening in the bar. So these are some disadvantages it has. So grizzly are used not only for coarser, um, for also for the roughest separation. Also, we can use the grizzly material, grizzly screening. So the next part that we also do the screening equipment, that is trommel. So trommel is nothing but a revolving screen. It rotates. It rotates either in a definite direction. It rotates. It consists of a cylindrical frame that's surrounded by wire cloth or perforated plate, which acts as a screening surface. So it is open at one or both ends and inclined at a slight angle to the horizontal so that the material is advanced by rotation of the cylinder. These units revolve at a very relatively low speed at 15 to 20 rpm, very slow. So a trommel is a mechanically operated screen consisting of a slowly rotating perforated cylinder surrounded by a wire cloth or perforated plate, with its axis slightly placed at an angle to the horizontal. So the perforation in the screen surface may be the same size throughout, or it may be different. Like at the initial, when the feed material is being introduced into the trommel, you can see the initial sizes are small. This is discard. Then it advances to the next part where the aperture is little bit bigger. So we can collect these two samples, two fractions, and these are the tail material. So that's why it is written that different sizes in which case, the small size perforation section is near the feed end. It is driven at the feed end through a gear mechanism. It has a feed point at the upper end and an undersized product discharge below the screen, and an oversized discharge at the opposite end or the lower end. So this one is the trommel that represent different size of perforations in a single cylinder. So how does it work? It works like the material to be screened that should be fed at the upper end and gradually that moves down the screening surface towards the lower end. In doing so, the material passes over the aperture and gradually that increasing size condition. So as the single cylinder is provided with lot of perforation ranging from the finest desired at the feed end and the coarsest designed at the discharge end, if the single cylinder is provided with a screen having three different size perforations, then we get four fractions completely, four fractions overall. So you can see this one. The fractions we get, uh, one is discharge, this one is the two sizes, and the tails, four fractions we get. The finest material is collected as the underflow in the compartment which is very nearer to the feed chamber, and the oversized material is withdrawn from the discharge end. Such type of arrangement is usually used for the smaller capacities. With this type of trommel, there is a tendency of blockage of the aperture by large material throughput, and the screen is with the finest opening being weakest, it is subjected to largest wear. The operating speed of the trommel is 30 to 50% of the critical speed. The critical speed is the one at which the material is being completely round in contact with the screening surface. So we operate at a 30 to 50% of the maximum speed that it can be. So that is known as that one is for trommel. The next one is the gyratory screen. That is another kind of screen that is being gyrated vertically, containing several decks of screen. Those are arranged one above another and held in a box kind of um, casing that I showed the picture in the second slide in this class. The screens are arranged in such that the coarsest screen will be at the top and the finest screen will be at the bottom. The discharge ducts are provided for the screens to permit removal of the several fractions. The casing is inclined at an angle ranging from 16 to 30 degree with the horizontal. The gyrations are in a vertical plane about a horizontal axis. The direction or the gyration in a vertical plane about a horizontal axis and is produced by an eccentric shaft fixed in the floor of the casing halfway between the feed location and the discharge. So the screens are rectangular and fairly long. The speed of gyration, the amplitude of throw, and the angle of tilt can be adjusted as per your requirement. The mixture of the particles is fed onto the top of the screen, and whole assembly of the screen and the casing will be gyrated over a time to make the particles pass through the screen opening and make it separate into different size fractions. The last one is the vibratory screen. This vibratory screen or the vibrating screen are commonly used in the industry where we deal with the large capacity and high efficiency we want. The vibration may be produced mechanically or electrically. Accordingly, we have mechanically vibrated screens or there can be electrically vibrated screen. So this vibration can be produced either mechanically or electrically with frequency of 800 to 3600 or even more as per our requirement per minute. These mechanical vibrations are generally passed on from high speed eccentric to the casing and from there to inclined screen so that the whole assembly is vibrated. Whereas the electrical vibrations are generally passed on from heavy duty solenoids directly to the screen, so that only screens are vibrating. So that is why it is different. The vibrating screen may be mounted in a multi-deck fashion, but generally not more than 3 deck in a stack, with the gorgeous screen at the top. That is the basic principle for screening, that the gorgeous screen will be at the top. Either it will be horizontal or it can be fixed at a little bit inclined 45-degree inclined position. So this one is the uneven load is being maintained. Feed is introduced in a kind of 45-degree angle screen placed. So this will be oversized, and then here it will just go down, and their way it follows the three stacked screen. The whole system is being placed on the spring so that it perform the vibrating of the screen, and thus the screens are effective enough for large capacity high efficiency for separating out the particles depending on their size. So in the next class we will discuss mostly as the size reduction part. So the thing we discussed in the class, that jaw crusher, cone crusher. So those kind of crushing equipment details we will discuss in the next class. So is there any question that you have further for today's session that we can take few minutes more? And this kind of that formula that I have shown, those formulas you can just write down in the paper, and you can just follow the steps that for how to make the table from the data in a perfect way, so that just you to take those data and do the calculation for the, suppose, average particle size or effectiveness calculation for the screen. And these are some basic also there is suppose you are in bachelor's doing btech, so this mechanical operation, unit operation, you have to plot some graphs for fractional screen analysis data or cumulative analysis data, and you have to calculate that d50 or d10 or d90 from that cumulative graph. Those are very common in doing the even in the practice for screen analysis. So if there is any doubt, then let me know that I can discuss. In the size reduction equipment,